Okay, hello everybody. Only one student here so far. Hi, Christopher, but more people coming. Okay, so start off the class, I'll just take a few minutes. I'll leave this up. If you have any questions, either about the assembly of the universal joint from the last 2 weeks, or if you have any questions about the homework, this part that I asked you to model between last week's class and this week's class. If you had any problems with those, if you have any questions, anything you want to talk about, feel free to ask. All right, so there's no problems with those. I guess we can get started. All right, so to give you a bit of a overview for what we'll be doing today, we'll cover a new topic, which is going to be importing files into Onshape. And after that, I'll do a little demo, and then we'll go over one of the parts for our Steam Engine project together. So I'll do a demo where I completely go through one of the components, and then I'll introduce the homework, which is going to be just another part on the engine. So we can keep that moving along so that we'll be ready to assemble that in a few more weeks. So getting into it, like I said, today's subject, today's new thing is importing files. And hi, welcome to the class. Yeah, today we're going to be talking about importing files into Onshape, but this is pretty common no matter what CAD software you're using. Whenever you're working on a project, you're almost always going to want to import a model that someone else has created. And this isn't just because like you don't know, it's not necessarily because you don't know or you don't want to create the model yourself, but a lot of the times it's just better to use models that are provided, for example, by a manufacturer, or if it's a standard component, it's good to use the accurate model for that component to make sure that when you actually try to build this thing in real life, that your parts are going to fit together, right? For example, screws. If I'm building something, if I'm trying to create a model in CAD of something that has a lot of screws, hundreds of screws maybe, there's no need for me to go and accurately create a model of a screw because they're out there, right? They're going to be more accurate probably than what I can do. And it just saves me that time. So if you're doing some kind of like engineering project where you're going to be working with standard hardware, not just screws, but things like bearings, other fasteners, machine components like gears or keys. In those cases, you're probably going to be buying them from some kind of vendor. So pretty common, I guess. McMaster is known for having a pretty big catalog, I guess. A lot of people do use this. There are, of course, other ones, but what's pretty cool about McMaster is that they provide CAD files for a lot of the software, for a lot of the parts that they sell. So for example, if I'm going to be using some kind of screw in my assembly, for example, for this air engine project that we're doing, right? It's going to have, if you're trying to build this in real life, you'd actually have to include a number of bolts or screws to keep it held together. And those things aren't going to be things that I'm making custom myself. I'm just going to buy some from a hardware store or from an online vendor like this. So what I might do is, instead of trying to create the model myself, I can just go through this catalog and figure out exactly which screw that I'm going to use, right? So I'm just clicking through the menus here, identifying what I want. And let's say that I end up needing, I know what I want. It's a, let's see, quarter 20 thread, inch long bolt with the socket head. So I figure out what part I want, and you can see when I go to product detail here, they actually provide, let's see, an option to download a file. So pretty standard, like universal file format for CAD files for 3D models. I'd say the most common one that you'll use is STEP, especially if you're working with like the CAD program. Another one that you'll probably see pretty often is STL. That's one that's often used for like 3D printers. Other ones, like I've seen IGES before. These other ones, like maybe if you use SolidWorks is good, but step file generally is going to work on, it's going to work in Onshape, and it's going to work in most softwares. So I just select as a 3D step, and I can download this screw. And you can see, just like any other file that I download from the internet, it's the same deal. And I can save it to some directory on my computer. And now I go back to Onshape. Let's say I have my document here that I'm working on where I needed that screw. What I can do is, in the same place where you add like new part studios or new assemblies, at the very bottom here, you can see there's an import option. So if I click on that, in the directory where I saved that file that I just downloaded, that's the screw. You can see it's a step file. I can hit open. I know some of you did this before to download the parts that I put on the Google Classroom. So it should look familiar. Here you have an option. This is only applicable in the case where you have a part that's consisting of multiple different solid bodies. So for example, if you have a bearing, like a ball bearing, you can imagine like a good CAD model of a bearing probably has separate bodies for the balls as for the inner and outer races, right? So a single part file might consist of more than one body. And this is just saying like, do you want to combine all those or not? So in our case, it doesn't really matter. Here, this is just asking questions about like orientation or things like that. So it doesn't really matter in our case, is all I'm saying there. So you can see once I do that, after a few seconds, it will appear at the bottom here. And now I have that model of the screw that I wanted, that I found from this online vendor. So you can see, like, I technically know enough about CAD to create this model myself, but it wouldn't be a great use of my time. And if I make a small mistake, then that could affect the other things I'm designing, because I want all of my other parts to be correct for this piece of standard hardware. Like a quarter 20 bolt is going to be the same no matter who you buy it from, where you buy it from. If it meets this standard for being a certain type of bolt, it's going to be interchangeable with any other type of bolt, right? So the same should go for your CAD models. All right, so there's a link in the slides. If you're in the Google Classroom, you can click on the link. There you go. It's also in the chat. It's also very short, so you can type it, but you can take a look, take a minute to look at the different things that are possibly interesting, maybe things that you would want to use in your own CAD models. For example, if you're very ambitious, you could choose to include all of the hardware, all of the screws and bolts in your engine model.
Can I ask a question about the universal joint, or do I have to wait until the end of class?
Sure, I'm taking a pause right now anyway. Yeah, go ahead.
So basically, the one problem that I forgot to ask last week was basically I did everything that you did except the last in the assembly in the last revolute. I click on what you told me and then I press solve, and then it just pops up a bunch of question marks on my mate features.
Okay, I'm not sure off the top of my head what the question mark means, but I would guess that that is something about the way that you created the mate is over constraining the assembly. Here. So in general, when you encounter a problem with assemblies, what I like to do is just delete the last couple of mates I created and go through all the mates and look at them again. I guess if you're having the problem right now, if you have it up, feel free to share your screen.
Look at this. So basically, I get the last revolute. I click on this, and then I press solve, and then it pops up these question marks. And I don't know why, because I did everything that you did. So like,
what happens if you just hit the green check mark there?
it's kind of weird.
I guess I can't really help you too much without going through each of the mates that you've already created, but I'm guessing just somewhere there's an issue with probably one of the cylindricals, but
Okay.
yeah, sorry, it's really hard for me to say without like going through everything in detail. But what my suggestion would be to
Deleting all the mates.
Yeah, that's generally what I do as well. Like if I can't figure it out after thinking about it for a few minutes, I just recreate my mates. And I know that doesn't sound too helpful, but it's just honestly sometimes what you have to do. All right, so if no questions about McMaster, I'll just do a quick example where this can be useful. Whenever you're designing rotating components like transmissions or like really anywhere where you have rotating components, right? So if you have wheels, if you have a motor, you're probably going to encounter a situation where you need to transfer rotation between components, right? And if you do that, you'll have a shaft and you'll need some interface to the shaft. You can't just have like a completely smooth shaft and do too much with that. One of the common solutions that you'll probably end up using is what's called a key in a shaft. So here, the shaft I'm referring to is this long cylinder here that goes through the middle. The keyway is kind of this square channel that's been grooved into along the length of the shaft. And then the key is this little, you can only see the square face of it, but it's a long, basically square prism that kind of locks the shaft to the thing that's surrounding it, which is in this case, the shaft collar. So actually this thing isn't really anything useful. You're just putting a collar on a keyed shaft, but you can imagine that this might be part of a larger assembly where in context, it might be something. So if you go to the slides, you can try this out for yourself and follow along, but I'll just show you. I kind of saved these links to 3 components that I could have picked out while I was designing a component, right? Like I could have decided that I needed a certain shaft. So I looked for it and I found these components. Now what I can do is instead of trying to recreate these models or something like that, actually all I need to do, since I'm going to be eventually buying these parts and they'll be coming to me exactly as they're modeled, the most faithful way that I can kind of create my assembly is to actually use the model that I know is going to be correct. So you saw I just went to the links. I hit download on each of the parts, and pretty easily I'm just able to import the components. So this two-piece shaft collar, I think this is an example where you have multiple bodies in a single part. You can imagine if you had this thing in real life, it would split apart into like two half rings that are bolted together. But it's pretty convenient for me to just think of it as one piece because I'm not going to take it apart while my assembly is in operation. So I'll actually just check this box that says create a composite part. I believe that will just turn it into a single body. Let's find out. There we go. Yeah, so I just have this one body here. I'll import the other two.
Hey, are we supposed to be doing this?
You don't really have to. I would suggest just trying to download one and import one. So you've done it before. The main goal of this segment is just to introduce you to the idea that you can download CAD of standard hardware. All right, and you can see as I go through these, models are entered into my document in Onshape. And this is the machine key I was talking about. So in my assembly now, if I want to use those parts, it's just like any other part studio that I might have created. I can just go to insert and put in my components. And if I click this to show composite parts as well, the two-piece shaft collar also appears. And there you go. So I can just take this and assemble them, whoops, like I might any other thing. So without too much effort, I was able to create this thing, which presumably I would then go on and create the rest of my more complex machine that I'm trying to design that makes use of these components. And so if you ever want to design something yourself that includes these kinds of machine components, you now have one resource. Keep in mind, like, there are tons of companies out there that sell products and provide CAD models of those products. So it's kind of like there's a whole world of libraries out there, basically, where you can just kind of virtually tinker with different parts, depending on what you enjoy. Maybe it can be amusing for you. All right, and before we go on, here's just one other thing. These like expansive CAD libraries of all different kinds of parts is not just limited to these like super practical standard hardware type things. There's also a lot of online communities dedicated to creating and sharing 3D models, right? So here's one example. It's called Thingiverse. So this is like a community surrounding like a 3D printing, like a 3D printer. So these people are people who like just create models and share them for each other to print on their 3D printers. So if you're into that kind of thing, like these generally are more fun or novel models that people create mostly for the purpose of printing. So if you're into that kind of thing, there's also tons of communities out there that are similar to this. You can go like look for them, but here's just one that happens to be fairly well known. And you can see like, I'm interested in gears. I clicked on this. I guess maybe that was a bit of an overlapping example with McMaster, but I'm interested in what this person created, which happens to be these helical gears. I can go in and somewhere around here, I can download. You can see in this case, it's not a step file, but an STL file. But Onshape will also accept STL files. So you can see, same deal, I can import that helical gear, and after a few seconds, it'll appear here. Now, one thing about STL files in Onshape is that they're kind of, like STL is a bit of a different way to save the information than a step file. You can see it's kind of giving you a lot of this. It's basically converted the surface into like a mesh of triangles. And so that's kind of what you're seeing here in Onshape with all this kind of crazy stuff. So if you're just trying to 3D print it, this is a pretty good format. But if you're trying to work with it for your own CAD models, it's perhaps less useful than other formats. But anyway, there you go. All right, so slides and all the links and stuff in them are on Google Classroom, so make sure you're in that if you aren't in that yet for whatever reason. And before we move on to back to the engine project, I'll just show you one more thing, which is kind of the opposite, the complement of what we've been talking about. Not only are you able to take other people's stuff, you can also give other people your stuff. So for the most general case, you're going to want to turn the model that you created into a file. So you've actually seen me do this a few times to give you guys like parts for projects. So like the U-joint stuff, I think I posted that on Classroom. Yeah, I posted that last week as step files, and you actually saw exactly how I did that. So what you do is you can just right click on one of these tabs for whatever part studio or assembly that you want to export. And at the very bottom here, there's export. If you click that, you can just specify your file name, your format. Again, step is pretty universal. I guess Parasolid, IGES, SolidWorks are ones I've heard of. Some of these are meant for like specific CAD programs like SolidWorks. And STL is one, for your 3D printing, it's usually going to be an STL file. So that's how you can send people models. I think Onshape actually has its own built-in community, kind of like Thingiverse, where people share files with each other. I think if you go to the public tab here, actually, yeah. So actually in Onshape right now, like you can just go to this public tab and you can see the latest things that people have been working on. I guess at this point, I should also probably mention that if you have like a free Onshape account, I'm not completely sure, but I think other people may be able to look at your creations. You'll have to look more into that on your own. I'm not an Onshape expert, but it's pretty cool just to see how other people are using Onshape. There's some pretty complex stuff in here, which is surprising since given it's like a browser-based platform, you might not expect people to do all these pretty crazy assemblies and models. And I guess one last thing, if you're working with other people who are also using Onshape instead of a different program, you can actually just share files with them using the share button. So it's kind of like Google, like the Google Suite. You can make documents public, you can use link sharing. The other day when I shared you guys that assemblies document that showed you all the different types of assemblies, that was something that I created with my previous co-instructor for this class, and he just created like a public link. So anyone with a link can look at that document. So you can also do things like that. All right. Any last questions about this whole importing, exporting thing? All right, if not, we'll go on to our project. So as I mentioned, like I previously taught this class with co-instructor. His name's also on the title slide. And for one of his high school classes, he actually created the air engine that we're modeling in CAD in like a metal shop. So you can see his model here. Maybe you can recognize some of the parts. The one that you did last week, or between last week and this week, is the big square on the bottom here. That's the base plate. So it's just a rectangle with 2 holes in it, right? Pretty straightforward, hopefully. No one asked me any questions about it, so I assume you didn't have any trouble with this guy. I said you can ignore the counterboards, so.
We did that last week?
Yeah, this was the homework from last week. So
oh.
Every week I'm just going to assign like 1 or maybe 2 parts to do, just so that by the time that we get to the end of this project, we can assemble everything together. I think there's a total of like 6 or 7 unique parts, and we'll be doing some of them in class together. So hopefully it'll not be too intensive, but still offer you some good practice every week. All right, so here are 2 more drawings. As a reminder, all the drawings are posted on the classroom, and you can also find them from their source at littlemachineshop.com. So probably the next 2 parts we're going to look at, I think it's a bit ambitious to try to do both of these in class, but I'll start with a cylinder. And so the cylinder is this kind of unintuitively, the cylinder is not actually a cylinder, like a circular prism type of cylinder, but it's called a cylinder because the inside of it is a cylinder. So if you are familiar with like a piston and cylinder, in almost all types of piston-based pumps or engines, you have basically a mechanism where you have a tube of fluid, air or liquid, and inside you have a piston, which is in this picture, the piston head is this black thing inside, and the movement of that piston head along the tube just creates a change in the pressure of the fluid. So you can imagine any kind of piston, basically you're compressing fluid by pushing it with basically just pushing fluid into a confined area to do something useful. And so the cylinder is that container. So here's the drawing. There's a few new tools that I'm going to introduce today, one of which is going to explain what all these words mean. Maybe when you look at this drawing, the first thing you notice is this peculiar call out here, which is 10-32 thread, 0.25 deep. That might mean nothing to you, and that's fine. The other thing that you might notice is that there's some callouts that have more than one dimension. So here, this whole diameter is called out to 0.500 on the top, but right below it, it's 0.501. So what that is a tolerance for the machinist in this case. if you're trying to build this pump, this engine in real life, you're going to be using some kind of tools on real material, and no matter what you do, you're never going to have an exact geometrically perfect object at the end of it, right? When you measure it again, after you've made it, there's always going to be a tiny amount of error in the actual dimensions of what you've created. And so the drawing here, by specifying these two numbers, is basically telling the machinist, the person who's making this part, that once you're done with it, this hole can be anywhere from 0.500 to 0.501. Basically, that it can be slightly a tiny bit bigger than 0.5, but it should not be any smaller than 0.5. And so in terms of our model, since we're not actually creating this in real life, whenever you see something like this, you can just choose one of the numbers. And since we use assemblies, we have tools like Revolute and Slider and such, it actually will have no effect on our model performance, since this is dealing more with like real life concerns. All right, and as to what this one means, I'll explain once we get there in our model. So this one I'm going to do as a demo, as I said before. I guess. So hopefully at this point, to do the homework, you created a document which will contain your project for the rest of the time you're working on it. So basically, I imagine that you have a document already that has a single part in it that's called base or base plate that contains this component. So make sure to go into that same document. No, Onshape is not connected. I'm starting a new document, but just go to the same document where you had the base saved. And while my Onshape is acting up, let's take a moment to review this drawing, right? So can anyone tell me, basically, I might have given it away already, but what the basic shape of this part is? What tools?
A rectangle.
Great, so yeah, rectangles. I see rectangles as well on all three views. So what tools would you use to create this part?
Line.
All right, so in the sketch, you would use probably lines. What about to go to 3D?
What?
What about to go to 3D? Which tools would you use?
These circles.
Yeah, you do need circles. As you probably noticed, there's a circle here, and then it extends with hidden lines into the body. So that indicates that there is some kind of blind hole or bore that goes into the part. Okay, my Onshape is not having a great time right now. Hopefully it will be good in a few seconds. Right, so yeah, everything that's been said is basically correct. We're going to start off with a rectangle, and we're going to extrude it into kind of a big block, big rectangular prism. And then after that, there's just going to be three things that we do to it. We're going to create one big hole that extends this way, and then we're going to create two small holes that are on another face of it. And as we get into these drawings that are meant for machinists, you're going to see some kind of peculiar things about it. For example, at the end of this hole, you see this kind of triangular hat, right? So this is just an indication based on the fact that people are going to create this hole using a drill bit. And if you ever used a drill bit, you know that the tips not that one, but the tip of most drill bits have this kind of pointed shape to them. So any hole that you drill, any blind hole that you drill using a drill bit is going to have a conical end to it due to the shape of the drill bit that was used to create it. Let me just sign into Onshape again. All right, so yeah, anyway, these pointed tips that you see in any blind holes are basically just going to be understood to be communicating, you know, like you can use a drill bit to create this hole. It doesn't need to be flat on the bottom. Because in real life, whenever you try to create a hole that's flat on the bottom, it usually requires a bit more work. You have to use something called an end mill instead of a drill. And sometimes it can require like a CNC operation. You need to use like more complex tools to create just blind holes that have flat bottoms. So in our case, we can just completely ignore all of that, right? We can either use a tool that I'm going to introduce called the hole tool, which allows you to actually just model these things automatically, or you can just ignore them, and either way, it's going to amount to the same thing. Maybe it doesn't like that document. I guess it just didn't like that document. Very interesting. All right, so let's get started with the demo. I'm kind of going to think of this like it's standing up the tall way. So I'll start off my first sketch in this top plane. And yeah, what I'll say here and going forward, like if I'm ever going too slowly or you don't want to listen to me and watch me go at my pace, you're always welcome to just look at the drawings and do the models on your own during the class. I'm just here to provide some guidance, and you can always ask if you have any questions. But yeah, feel free to work ahead. Like if you're very accelerated, you can try to finish the crank wheel too. All right. Anyway, top view, I'm looking at this view of my drawing. And first thing I'll start with is this 1 inch by 1 inch square. So I have my rectangle tool. And by now I have a pretty good idea of how to make a square. I can actually just use my relations, select the adjacent sides and make them equal. And with my dimension tool, I can say that's 1 inch. And I'm actually done. That's all I want. So that's my top view there. And then to extrude this square into a prism, I see from this front view, I'll call this the front view, that the height of this block is going to be 1.875. So I'll pick my extrude. And I'll type in a depth of 1.875. And this here makes up pretty much, this is the main body of it, right? All the other features are kind of cut out of this form. If you're making this in real life, you'd probably start with a block that was about this size, maybe slightly bigger. You would just trim it down to be these exact dimensions, and then you would drill a few holes into it. Okay, and now I'll do this big bore, the 0.5, the 1/2 inch diameter bore. And I'll introduce a new tool that you can use when you're doing things like this. So I'll go look at the bottom of my part. You'll see I'm looking at the bottom, and I'll create a sketch on my bottom face. You can create the face, like you can select it just by clicking this face. You can also, in my case, just use the top plane, I believe, yes. It amounts to basically the same thing. And then I need to locate this hole. So what I'm going to do here, instead of creating a circle that I'm going to extrude with the remove option, that's how we've created holes up to now. I'm just going to create a point that's in the center location of the hole. In that center location, you can see that there's a center line in blue that runs across here. And I can see that the center of the circle is 3/8 of an inch away from the left edge here, 0.375. So I'm going to create a point. If you haven't seen this yet, this is the point tool. It's kind of off to the right, maybe in the middle of your first group of sketch tools. And to create a point, you just click anywhere and you get a dot. And the point is completely unrestricted. I can drag it anywhere. What I'm going to do is the same trick that I use to center things. So if I create a line and I start it at the midpoint of the left edge and I connect it to my point, then I'll make this a construction geometry and I'll make it horizontal. Now this point is kind of constricted. It can only move horizontally along the middle of my square. And then to get that 3/8 inch from the left, I just add a dimension. That's one way that you can create that point. But my objective here is just, all of that was just to get this one point here that's in the correct location. That's where my hole is going to be.
Wait, can you do that? Like, can you do like the last few steps again? Like the, oh no, wait, no, never mind, I know.
All right, great. And here's where the new tool comes in. We're going to use the hole tool here. This is probably a new one for most of you. But if you look in this second group of 3D tools, the same group as fillet and chamfer. Those you've probably seen before, but we have our hole tool. So if you click on that, it brings up this, again, another dialog box. And this one might seem a bit complicated, but don't get too overwhelmed. Basically, we're only going to interact with a few things. So the first one is the style. And here you might recognize the words counterbore or countersink. When I was explaining the example for the homework from last week, you noticed how these holes kind of had two layers. There's a big hole on top and a small hole kind of going through the center. And I explained that's a counterbore that's used to allow the heads of your fasteners to lie under the surface of your part, right?
Yeah, how did you get your hole again? I don't see it on my screen.
Hole is just one of the tools. Depending on the size of your monitor or the aspect ratio, you might, it might be in it like a drop down, but it's just this tool. If you can't find it, you can also just search for it. At the far right, there's a search tools bar. And if you just search hole, it should come up.
It doesn't come up. It says there are no items that match your search.
All right, interesting. Are you in the sketch still?
Yeah.
Okay, you should be back in the, yeah, just accept the sketch, come back to 3D
Oh no, wait, no, no.
workspace.
Yeah, I got it. I got it. But I don't know how to make my construction line straight because it's slanted.
I used a horizontal relation on it.
Okay, there you go.
All right, so back to hole. Basically, Onshape gives you the option. Simple just means it's a hole, like nothing special, just a hole. Counter bore creates that little head on it. You can see the icons here. And countersink creates like a tapered version of a counter bore. It's that little chamfer kind of that goes at the end of your hole. So we don't want either of those. We'll just go for simple. Next, this one should be familiar to you from our extrusions. So through means it goes all the way through, and blind means it doesn't look where it's going. It just goes exactly as deep as you specify with the depth. So in this case, we want a blind hole because we know the depth that our hole should go to. And looking at the drawing, the depth is actually marked out here. It's 1.625. So for the depth here, I'm just gonna type in 1.625. And now this is where you see a bunch of stuff. And you probably don't know.
I don't see that much stuff.
Yeah, so you might not see it if you're in like custom, right?
No way, I got it. I switched to what you did.
Yeah, so all of these words like ANSI, ISO, DIN, these are standard organizations. They're organizations that maintain basically a set of rules for how everyone in the world should manufacture and design their things like screws, right? Because you can imagine if everyone in the world designed screws their own way, then nobody's screws would fit together, and that would be kind of a problem. You'd have to buy all your hardware from the same manufacturer, which is unrealistic. So these organizations create these standards that tell you exactly what sizes and pitches, different drills and holes and threads should be. And the idea is that in your CAD, you should make your model match those standards, and then everybody's hardware, all these bolts you can buy at the hardware store will work with your part. So that's the idea. ANSI is probably the one that you'll be using if you're in America, maybe ISO as well. I think, yeah. In our case, we're just gonna go to custom though. So custom is the first one in the list. I guess it might be the default, seeing as some of you didn't see ANSI by default. But in our case, we're just gonna call it a custom hole. And the diameter of that custom hole is going to be 0.5. The depth, like I said before, is going to be 1.625. And that's all there is to it. That's my hole. And the last thing I need to do is tell Onshape where to put this hole. And that's where the point that I just created a moment ago comes in. I can just click on this point that I made. And you can see in the preview that it creates that hole that I wanted. I didn't have to do any extrusions. I didn't have to create the circle. I didn't have to do any of that. All I did was specify the diameter, the depth, and tell it that it was a simple blind hole, right? So you can imagine this is pretty powerful. This may have seemed kind of like it might not seem that useful from this example, since you could have easily just created a circle and extrude removed. But as we get into more complicated holes, you'll start to appreciate why this is useful. The other thing is you can see at the bottom of the hole that you have kind of that conical tip to it, like a pencil, like kind of like you pushed a pencil into a piece of clay. And that's what I was saying before about how drill bits create that in a part. So Onshape just creates that for you. You didn't even have to think about it. It just happens automatically.
Can you show me the hole again? Because I was trying to figure out to convert because I'm in centimeters. I was trying to figure out how to convert 0.5 inches to centimeters. Oh no, wait, since I'm already using, wait, no, never mind. Okay.
Yeah,
Because,
don't worry too much about units. I would say if you're in centimeters, just type in the exact same numbers. Just type in like 0.5 and 1.625 and don't worry about converting
and
since
then
we're not trying to make this in real
what
life.
do I click on to start? Oh no, wait, never mind. Do I just do that? Okay, I got it.
All right.
Why is it not centered though?
The hole will just appear on whatever point you scope it to.
Was it supposed to be centered?
Your hole is supposed to be centered along one direction, but not along the other direction.
Oh.
So the center is 3/8 of an inch away from one edge, and it's centered with respect to the other edges. Anyway, back to the drawing. Don't have too much time, so I'll kind of move us through this. The only thing we have left in this part is these two holes that go through the side. You can see one of them joins the original big hole that we just created, and one of them is blind and it stops just short. So these holes also both lie on the same plane, I guess. And the important thing to notice here is that the holes come in from the side where the hole is like far away from, right? Like if I'm looking at this, it's symmetric left and right with respect to like the line of symmetry here, but it's not symmetric with respect to these two. So we're going to be careful to pick this face and not this face. So this one, since that's how it is in the drawing.
We're going to pick the one that's side is farthest away from the circle? Yes,
indeed. And on that face, you're going to create a sketch. You can see this is my sketch plane, sketch 3. It's on this face that's far away from the hole. And I'm going to do the exact same thing. I'm going to create 2 points. So I'll start off just with my construction line. I'm going to create it on, I'm just going to connect the 2 midpoints of these lines. And you can see that automatically fully defines it. It comes out black. I'll turn that into a construction line. And then I'll just look at the locations of my 2 holes. One of them is 0.875 from the bottom. The other one is 1.5 from the bottom. So I'll just plot my 2 points along this construction line. And I'll use my dimension tool to tell Onshape what dimensions to use. And so just like that, that's all I need to do for my sketch. Things to note, again, I'm on the face that's farther from the hole, and my dimensions come from the same side as the opening of my hole. So I don't dimension from the top here, I dimension from the bottom where the hole is.
Wait, never mind.
All right, and I'm going to now just drill my holes again using the hole tool. So the one on top, the one closer to the closed end of this cylinder, that one has a diameter of 0.125. This symbol means diameter, if you haven't picked up on that. And looking at this cross section, well, not really cross section, looking at the side view here, this front view, you can see that it just connects into this hole from the outside. So I only need to go in. It doesn't say how deep I should make the hole, but I just need to know that it goes in deep enough to fully connect with this channel here.
Wait a minute.
So what I'll do, same thing, hole tool. It's going to be another custom hole.
Can you spin your thing around for a second? I don't know if mine is on, because my dot, like the top dot, is closest to the circle. Oh, I did it upside down. Okay. So
I'm
like
do the exact same thing as I did for the other hole, except here I have a bit of a thing going on. I can't use through because that goes through everything. So I'm just going to use blind. And the distance, the depth that my hole needs to go is deep enough to reach this bore, but not too deep to go out the other side. So looking at the drawing, I can just do a bit of quick reasoning. To go in this far, let's say I need to go in like 1/2 inch, which will get me, you can see now that gets me through all the way to the bore, but it doesn't get me past to the other side.
Wait, which dot am I supposed to click on? The one that's at 1.5?
Right, just like it is in the drawing. Yeah.
That's the only one I have to click on, right? I don't have to click on the 0.875. Yep. Okay.
After that, we're going to create the other hole. You can see whenever you create a feature, you probably noticed this already. Whenever you create a feature with a sketch, Onshape has a tendency to automatically hide that sketch, so you can't see it anymore. And that's just so like your stuff isn't cluttered. Because in general, you have one sketch and you make one feature out of it. Sometimes you want to use the same sketch to make more than one feature. So what you can do is just, if you hover in your feature tree over something that's hidden, like sketch 3, if I hit that crossed out eye, I can make it a not crossed out eye, and now I can see the sketch again. You can see it shows up again. And I'm going to do the exact same thing, just in this time, this is where we kind of use the abilities, the powers of the hole tool. This hole, this doesn't tell me a diameter. It just tells me that it's a 10-32 thread, 1/4 inch deep. So what exactly does that mean? I pull up my hole tool, and this time I'm going to go from custom to ANSI. Simple and blind still. And so I can explain this further in greater detail next time, but the main idea is 10-32 thread specifies the diameter and the pitch of a screw. So a tapped hole, a threaded hole, just means that it has it means it can accept a screw, right? You can screw things into it because it has those threads. We call these threads that the bolt can fit into. And so instead of clearance, we're going to call it tapped. And we know it's tapped because it says the word thread here, right? 10-32. Even if you didn't know, even if it didn't have the word thread there, 10-32 implies there's a thread because the second number is a pitch. And if it doesn't make sense to you, don't worry about it. If you're curious, you can read more about like tap standards or thread standards. The important thing is getting the numbers. So 10-32, that's all that means. Don't worry about diametric engagement. And you can see it automatically fills in the diameter for you, as well as the, yes, don't worry about these.
Mine are different than yours.
Make sure you're in ANSI.
Yeah, I am in ANSI.
And tapped.
Yeah, I'm in both, but mine are different than yours.
I'm not sure what you mean by different.
Like the numbers are different.
You can just type in what you want for the depth. But make sure you're also in number 10 and 32 threads per inch.
Wait, does it matter what the numbers are?
Yeah, the numbers do matter. This refers to the diameter. So instead of calling out like a specific diameter, it just tells you it's 10. So 10 just means it's meant for a size 10 screw, right?
So what are the numbers supposed to be?
10 and 32 threads per inch, like
No,
I have in mind.
Like the bottom numbers that say like 0.159 inches, 0.25.
Right, these are correct. And these are filled in automatically by Onshape. If we didn't have this whole tool, you'd have to do these manually by looking at what's called a tap and drill chart. So in most like engineering or machinist reference books, you'll find tables similar to this, and they'll just tell you exactly what all these things mean in terms of diameters. But if you don't want to deal with that, Onshape's whole tool is a pretty useful tool because it just lets you fill in the details of what it is, and it'll put the numbers in for you. The only number you change is the depth here, which is 1/4 inch. and you place it at the location of that other hole. And when you do that, basically, there you go. That's the end of the part.
But my other hole is gone.
Make sure you actually created 2 different hole features and didn't edit the first one you did.
Like there's nothing to click on.
All right, I can get back to you in a minute. We're just gonna wrap up the class since we're already running late. We'll get to the crank wheel another time as another demo, probably next week. For the homework, by next class, I want you to work on the piston and complete it. The drawing is on this slide and also on the Google Classroom. Note that the drawing has these tolerances that I mentioned before. We have these 2 numbers stacked on top of each other. Don't worry about those, just pick one of the numbers, pick any arbitrary number that's between them. I don't care. It won't matter for your assembly as long as you have like something that's in the range of those numbers, right? So there you go. I'll see you again next week. For those of you who need to leave, if you have any questions, I'll stick around for just a couple more minutes, but that's all I have for you. So yeah, thanks for coming.